Before I consider the derivative of y equals tan of theta, first of all I want to look at the graph of the tan function. The graph of the tan function can be generated from a unit circle, where theta is an angle. Increasing theta is measured anti-clockwise from the positive x-axis in our unit circle. So a unit circle has a radius of 1, so you can see here the radius marked in, it's 1. And to get the tan of 45 degrees, for example, we construct a right-angled triangle with a tangent drawn at this point here, and the tangent is cut off by this line here. So we want the length of this tangent. The tan of 45 degrees is the side opposite 45 degrees, which we're calling y, divided by the side adjacent to 45 degrees, which is 1. But y divided by 1 is just y. So you can see the length of the tangent cut off by this angle is the tan of 45. So the word tan literally comes from tangent. Now, you can imagine building up a graph of values for angles running from 0 to 90 degrees. You can imagine increasing theta, say to this value here. Then we'd have to find the length of the tangent cut off. So we'd have this value here, corresponding to some angle between 45 and 90 degrees. So you can see that as theta runs from 0 to 90 degrees, we have an increasing function. Actually, the length of the tangent blows off to infinity as theta approaches 90 degrees. So the tan of 90 degrees is infinite. Okay, because you can imagine, imagine we had an angle of 89 degrees. We'd have some line like this, and it's going way off here. The length of the tangent keeps on increasing indefinitely. So that's what's happening to the curve. So the curve is approaching this vertical asymptote. As theta goes beyond 90 degrees, what happens is the tan becomes negative. The tan is defined to be negative for angles in this quadrant here. But it's the same basic idea. We would be constructing a tangent, getting the length of this side here, but we make it negative. So we'd have negative values here until we get to 180 degrees. When we get tan of 180 is actually 0. And then from 180 to 270, the tan is defined to be positive. Now I explain why that is so in other videos, so I won't go into that. That's in the trigonometry section. But we get a periodic curve. So this pattern here is repeated in intervals of from 90 to intervals of 180 degrees. So we have a period of 180 degrees. So we're interested in the derivative of y equals tan theta. So you can imagine an angle theta somewhere here. I'm going to call it theta because I've already used x and y when discussing this unit circle. The derivative, as I've explained in several videos, is just the slope of a tangent to the curve. I've decided actually to change theta back to x. Now I'm not going to explain geometrically what's going on. I've done that in a few times in other videos. What I'm going to do is write tan of x as sine x over cos x. That's what it is, identically. And we calculate what's called Newton's quotient. So we work out f of x plus h. We just replace x with x plus h. Then we subtract f of x, that's tan of x or sine x over cos x, and we divide by h. So what I've done is combined these two fractions here by getting a common denominator. That is, I've multiplied the two denominators of these fractions together. So here's the common denominator. The next step is to divide the denominator of the first fraction into the common denominator, which will give the other denominator cos x. Multiply cos x by the numerator, which is sine of x plus h. Then we have a minus sign. Then do the same here, divide this denominator into the common denominator, which will give us the other denominator, cos of x plus h, and that's multiplied by the numerator, which is sine of x. Basically, we're multiplying this by this and this by this on top here. And the next thing we shall do is, well, divide it all by h first of all, but look for an identity for all of this thing on top. Now, as it stands, if we were to take the limit as h tends to 0, we'd get 0 over 0 as it stands. can check that yourself. If you let h go to 0, you get 0, you get sine x, you'll actually get tan x minus tan x, which is 0 over 0. That's indeterminate. So we need to consider an identity for what's on top here. This thing on top has the form cos A sine B minus sine A cos B, where A is equal to x and B is equal to x plus h. So you look in your tables for an identity that has this form. Actually, a better way to write this is if we write A for x plus h and B for x, then this, well, it doesn't appear like this in your tables. In your tables it'll appear as, well, I'll write it down actually how it appears in your tables. We have sine A minus B is sine A cos B minus cos A sine B, which is exactly what we have here. Now if I did it the other way, well, we'd still get the same thing. I just have to interchange A and B. That's all. So, you know, B would become A would become B, but the upshot would be exactly the same. So this is the identity that we have to apply. So this is what we get, sine of A minus B. So what's A and what's B? Well, A is x plus h, and minus B is x. So these x's cancel. Now, so we get sine of h over cos of x plus h times cos x. So here we have it here, sine of h over cos of x plus h times cos of x. But all of this fraction on top is divided by h. That's equivalent to multiplying all of this fraction on top by 1 over h. Okay, so I've written, and I've also factorized this out a bit. I've written sine h over h, which is here, and then we have 1 over the cos of x plus h times cos of x, which is this thing here. The reason I've done it like this is because I'm going to exploit an identity that was covered in previous videos. As h tends to 0, we have to get the limit as h tends to 0 of this, of Newton's quotient, to get the derivative f prime of x. This thing will tend to 1. And here h will go to 0. So this h will go to 0. So we end up with 1 over cos x times cos x, or 1 over cos x squared. So I've written it up here. So this goes to 1, as I said already. As h goes to 0, that's a standard limit. As h goes to 0, we end up with 1 over cos x times cos x. Cos x times cos x is written like this, cos squared x. Now 1 over cos x is sometimes written as sec x. So we have 1 over cos x times 1 over cos x here. So we have sec x times sec x, or sec squared x. So this is the derivative of tan x. Finally, I want to consider the derivative of the function y equals cos of x. So our function f of x is cos x. Here's Newton's quotient. We want f of x plus h minus f of x over h. So we want the cos of x plus h minus the cos of x over h. Now in this form, the limit will be indeterminate. As we let h tend to 0, we'll get 0 over 0. The top will be 0 and the bottom will be 0. So we need an identity for cos of x plus h minus cos of x. So if you go to your tables, you'll see an identity of the form cos A minus cos B. So here's the identity. So you can see that A is x plus h and B is x. So we have minus 2 sine A plus B divided by 2. So that's x plus h plus x divided by 2. Well, x plus h plus x is 2x plus h. We divide by 2, and then we multiply by the sine of A minus B over 2. So that's x plus h minus x. That's just h over 2. And we divide by h. And this is the derivative of this function is very similar to getting the derivative of y equals sine of x. We will be using the fact that the limit as h tends to 0 of sine of h over 2 divided by h over 2 equals 1. Okay, whether it's h or h over 2, it doesn't matter, because as h goes to 0, h over 2 will go to 0. As long as both of these go to 0, then the limit of this function here is 1. So we have sine h over 2 in the numerator. So we want it in the denominator, so we just put this over 2. And then we compensate by multiplying by 2, just to make sure that the 2's go out, we haven't changed anything. And if we do some breaking down here, of course we leave this intact, because we're going to be factorizing this. These 2's will cancel, so we get minus sine 2x plus h over 2 multiplied by, now I'm going to write sine h over 2 over h over 2, so I'm going to stick the h over 2 in underneath this. So this is very similar to getting the derivative of y equals sine x, a similar approach. Now, if we let h go to 0, if we take the limit as h goes to 0, what happens? Well, if this h goes to 0, we're left with minus sine 2x over 2, or minus sine of x, and of course this thing goes to 1. So here's the answer. So if y equals cos of x, the derivative f prime of x, or dy dx, is minus sine of x.